In yesterday's Fender FAQ video, I was not very satisfied with the very cursory and rough explanation I gave of how a tone stack works. And if I were a guitarist who really wanted to know what those knobs were doing behind me in that big box I bought, I'd want to know more. So here, let's get into the more. And I promise this won't be very deep. We're not going to go down too many rabbit holes. You won't have to take notes necessarily. There's not going to be any math. We're going to keep it pretty straightforward as much as I can. Before you can understand how a tone stack works, you need to know one really important part of how circuits work, at least the circuits that we use primarily for audio. And that's called an RC filter. And that filter is made with a single resistor and a single capacitor. And here on the screen, we've got the input and the output points shown. On the left, the input coming signal goes through a 500 picofarad capacitor to the output, but that output also has a 500K resistor to another point. That's usually ground in an amp or in a guitar, it's almost invariably ground. It can also be a cathodione elevated voltage. It can also be a half voltage reference point in a pedal. It doesn't really matter what this is for this point, because the important point is you have a capacitor followed by a resistor going to another point. That means that everything at our output point above a certain frequency is going to pass through the output, and everything below that certain frequency is going to want to go over here. And in a lot of cases, that's to ground, so that those frequencies just go away. The frequency is chosen by the value of the capacitor and the value of the resistor. So in this one, where we have a capacitor and then a resistor going to ground, let's call it that, everything above 637 hertz wants to go to the output. Everything below 637 hertz wants to go to ground or to the other destination. On the right, we have the reverse of that, where we have the resistor first, and then there's a capacitor, which means that everything below 637 hertz wants to go to the output, and everything above 637 hertz wants to go here. And if this is ground, those frequencies just go away. This is the core principle behind how a guitar tone pot works, and it's something that we'll use a lot in other aspects of amplifiers. On the left, though, is the primary way we do things in guitar amp tone stacks, with a capacitor followed by a resistance to ground. The next thing you need to know, this is called a parallel RC filter. And by itself, if we ignore the 500K to ground over here, you would have a slight accentuation of frequencies over 637 hertz, because that is an easier path for the audio frequencies to go through than the resistance, because a resistor resists the flow. And for those of you who are going to jump on every little word I use, I know current and voltage and all these things are different, and there are different verbs one can use. From a guitarist point of view, think of it like plumbing. Everything above 637 hertz wants to go this way. Everything below 637 hertz wants to go this way. It's going to get a little bit of attenuation from that. But when we have this resistor followed by this resistor to ground, this forms a voltage divider. This is how a guitar volume pot works. This is how most volume pots and amps work. And so at this point, if the capacitor was not present, all frequencies would be attenuated by the same amount at this junction of the voltage divider. But because we have a capacitor on the top part of it, all frequencies above 637 hertz will not be attenuated at the output, and all frequencies below 637 hertz will be attenuated. And that's how you get a treble emphasis, and that can be subtle or extreme depending on the ratio between the capacitor and the resistors and where in the pot's travel it is. Because if you have a 1 meg pot, only at one location on that pot is at 500K, 500K. It's going to be all over the map what the ratio actually is. And so they're very interactive. If I didn't already mention this, again, this is not a steep filter. It's not like there's a hard and fast cutoff. Oh, you get everything above 637 hertz full tilt. You also get emphasis of things below 637 hertz, which will get less attenuation. But that dividing point is subtle enough that it actually works very musically for us. So we don't really have to worry about it too much for guitar amps. If you're designing something to measure, I don't know, transmissions from Saturn, you may want something very, very precise, and you've got other ways around distortions and nonlinearities. But we're guitarists. We like distortion and nonlinearities. The next really important thing to know is when we take that information of an RC network, we can have a guitar amp stage, and this is pretty much what happens in a Fender, most Fenders from the 60s and 70s. And the output of this plate, which is the first gain stage, goes through a capacitor to some kind of load. In this case, I've shown a 1 meg volume pot, and then to the next stage. And so by choosing the value of that capacitor and the value of that pot, we can choose how many, at what point the lows are rolled off, the frequency above which all signal is passed. So I just chose arbitrarily here a 22 nanofarad and a 1 meg, and that's very common to find in guitar amps. And I've shown here 7.234 hertz. Now, this is the value that this RC filter by itself gives. This is not what you actually get in a guitar amp for reasons we're not going to go into too much, other than to say there's a parallel resistance of the plate, of the tube, that varies with the plate resistor, the tube type, the individual tube, the voltage is present, and then the impedance of the next stage. But when you just take the capacitor and the resistance together, this gives us this number, and it's fairly useful for looking at the differences we're going to look at now. So here we have 22 nanofarad and 1 meg. If instead we used a 2.2 nanofarad and a 1 meg, that changes that high-pass frequency from 7.234 hertz to 72.34 hertz. So you're still going to have the low E present on a guitar, but all the stuff below that gets filtered out. And there's not a lot of audio information below a certain point that you want in a guitar. Now, 72.34 is going to give you your fundamental, but it's not going to give you the undertones. So you may want to choose something more along the lines of an octave below the low E on a guitar, which is 80, 81, 82 hertz. So aim for 36 to 40 hertz for your high pass point here, and you'll have a very full low end, but you won't have the flub and all the subharmonic information that happens when you brush the strings with your skin. But this is just really to show that going from a 22 to a 2.2 while keeping this resistor the same has also moved that high pass frequency up by a factor of 10. So from 7.23 hertz to 72.34 hertz. And for subsequent parts of this, I'm not showing the input jacks and some of the other stuff, just for clarity. We're going to be focusing on what's happening here between this triode and this triode. I'm going to go to the other one again. So you saw what happened if we had 22 versus 2.2. Well, are there other ways to get this frequency response? Why not use a larger capacitor and a smaller resistor? Let's show that. Here I've changed that 22 nanofarad cap to a 220 nanofarad cap. That's a 0.22 microfarad. But I've decreased the resistor by the same amount, same proportion. So that went up by a factor of 10. This went down by a factor of 10. So now we have 100K. And we still have 7.234 hertz. So why do we typically find a 22 nanofarad and a 1 meg rather than 220 and 100K? Well, part of it is that 220 nanofarad caps used to cost a lot more than 22 nanofarad caps. But the most important thing is what's called loading and load lines. So this tube, this 12x7 stage with 100K plate and 1.5K cathode bypassed by a 25 microfarad cap with the same voltage supply. So if this stays static in both situations, this has 10 times more load on it than the first example. 100K pot puts 10 times more load on this which means that this will drive the next stage less efficiently. You'll lose gain. It won't. The signal doesn't want to flow quite the same way. And again, I'm going a little vague, talking more of musician language than a text language. This is not a very efficient circuit. You'll get less gain. You'll get less pleasant behavior of the signal swing through the tube and onto the next stage. So typically, we want to have the impedance of a plate-driven stage fairly high. So 100K is too low, even if we can get the same frequency response by using a larger cap. So that's why you'll usually see a 1 meg or higher load whenever, or sometimes 500K, but rarely will you see a 100K volume pot in an amp because that's just too much of a load to put on the preceding stage. And so we say, what is the load we want? 1 meg's typical. It's actually going to vary depending on the input of this and all the stuff over here, but we'll just say 1 meg. So you choose the capacitor that gives you the frequency response you want with a 1 meg. And again, I think a lot of guitar amps traditionally go a little bit overkill on that because they weren't just designing guitar amps. They were for bass, accordion, all kinds of stuff that they could sell you. Some instruments had much larger, wider frequency response than guitar. So you could take the same circuit with 1 meg and go down to a 10 nanofarad or 4.7 nanofarad and still be pass everything below, an octave below your fundamental guitar, but you're just not going to have that 7 hertz stuff, that 10 hertz to 20 hertz stuff that you won't even hear. But that's outside the scope of this video's intent. Anyway, so now we have how an RC filter is often incorporated in guitar amps, and that combination chooses the frequency above which signal is passed, and the concept of having certain values to put certain loads on the preceding stage. Let's go to the next part where it gets more interesting. Here you can see a very basic concept of how to modify the tone. They've just added a bright cap here. And that means when this volume is turned down, the treble frequencies are not attenuated, but the bass frequencies are. And as you turn it up, they're attenuated. The bass frequencies are attenuated less and less, and the treble never was really. That's one level, and that's the parallel RC value in conjunction with the voltage divider, like I showed you before. And here, in addition to this bright cap here, we've added a variable treble roll-off, which is the resistor in series with a capacitor, which is in parallel with this capacitor to ground. With this resistance to ground, which is this volume pot. And so this rolls off highs. And as this resistance is increased, as the tone pot is turned up, fewer highs are passed to ground, and everything just goes this way. But as this is turned down, everything above a certain frequency wants to go to ground, like we discussed. The next iteration of this, where you have a treble roll-off and a treble emphasis, but this side of the pot is not used, is to attach this part of the bright cap to the unused side of the pot. So when this pot is on 10, this bright cap is connected right here to the input of the volume pot. So there is no tone roll-off happening. And as this volume pot is turned down, this bright cap does more and more. But as you turn this tone knob to the center, some frequencies are sent to ground here, and fewer frequencies are sent to the bright cap. And as you turn this tone circuit more counterclockwise, more frequencies are sent to ground, more highs are sent to ground, and you're not getting any benefit. No frequencies are really going through this 500 picofarad bright cap. This is the core idea behind the 5E3 tweed tone stack, really just a tone control. But it was a very elegant thing. You'll see variations on this from other manufacturers. With one additional pot, you can roll off the highs in one direction, you can add in highs at the other direction. Those added highs are only apparent if this is at relatively low volume. So once you turn that volume up above 2 o'clock, this will do less and less. But It was very elegant and remains a very musical set of controls to this day. But what did the Fender do after that? We're going to ignore some of the relatively odd things that Fender did in some of the Bassman and Twins from 57 through about 62, because he went in a couple different directions, tried some different things. The Tonestack from the 5F6A we'll get to a little bit later in this video, or at least mention it and why it's pretty much similar to what we're going to be talking about later. But in the video yesterday, I mentioned the concept of different frequencies having different volumes. Like you have all your mids with a volume pot, all your trebles with a volume pot, all your bass with a volume pot. And you could actually do that. You could build an amp just like this that would do that. You'd have all the frequencies above 6.37 hertz on this volume pot. And by choosing the value of the pot, you're not just affecting the frequency, but also the load. So this would be relatively inefficient. So you're not going to have a ton of maximum 30 hertz available, but there'll be some. And it'll be stronger at the higher frequencies that take less energy to drive. You could control your mids here with a 10K. That's very inefficient, a big loading issue. But you will be able to blend in the stuff from 338 up. And then you could have everything above 1.72K hertz here with a much larger resistance. So you're going to have more emphasis to the upper mids. This is going to be the most efficient of the three. Though doing it this way with three different loads, all in parallel, that still drives this preceding stage fairly inefficiently. And I showed some mix resistors here just because I had to. It would kill me to put any kind of schematic out there where if anyone turned any one of these volumes to 0, you would get no signal. This is why they came up with mix resistors. So if anyone wanted to try this idea as a build, you'll see that it works. It's not as good as what Fender started doing, which I'll get to next. But this is the literal implementation of what I described in the video yesterday as an analogy of three different frequency sources with three different volume pots being blended together. What Fender actually did was much more clever. You'll see that it branches to three different capacitors like the other one. We'll talk about this resistor in a moment. And instead of having three mix resistors, these volume pots for the different frequencies are also all connected together. So they also act as mixers. So you can have your treble control, your bass control, and your mids control. And they're all mixed together through the treble pot. And again, like I showed you in the other one, the treble pot from this point to ground, 250, 250, 10K. Depending on where everything is set, that's about a maximum of 510K, a minimum of 500K. So you can actually have, you have more you have a more efficient load on this treble cap than you do on these. So the treble will tend to be emphasized. And it's not just getting treble, it's getting the upper mids as well. The mids cap in a Fender is really a lower mids cap. And the bass just sets the real deep stuff. But if you do this circuit without this resistor, you're going to have way too much low-end sludge. So Fender and other companies added this resistor, which we call the slope resistor, which attenuates the signal going to the bass and mids while letting it be strong going to what we call the treble, which is really upper mids. It gets the 5K along with it, but it's probably 700 hertz area and up. And it's hard to draw these things out and know which frequencies because it depends on a lot of factors and the pots where they're turned. So I could put very accurate numbers on here if the pots are all turned a certain way. And if any one of them changes, all those numbers change at once. It's a very complicated thing, and I'm not trying to do a full dissertation. So let's not get down into the math and the whatabouts. But the previous example of the volume pots is still here. And the mix resistors are still here. And the load concept is still here. And this fine-tunes the blends between the lows and ultra low, the lows and low mids with the upper mids and treble. And that can be varied, and it is varied a lot in Marshalls. These impedances, these resistances can also be varied. A Marshall will usually have a 1 meg instead of a 250K for the bass, though it has fewer bass frequencies going to it because they decrease that cap value. But that also gives this entire stage a much larger impedance, so the previous stage has a little more gain. More on that in a moment. Anyway, the output of these Fenders goes to one more volume pot, which either has a fixed bright cap, no bright cap, or a switched bright cap. We already discussed how a bright cap works, and goes to the next stage. Now, this is what you find in all the black panel and silver panel Fenders. And the brown panel era was a combination of things like you'd find in the 5E3 that I discussed before, and an earlier version of the same circuit that you see here. The treble pot was a little more complicated, and there was a fixed roll-off to ground for highs after that, but still the same core idea. Now, the earlier 5F6A Bassman and Tweed Twin used a cathodiene follower to drive a very similar tone circuit to this. They had the volume, ignore this tone stack, so you have this, get to a volume, to the next stage. There'd be one more stage where the cathode would drive its tone stack. But the genesis of this 60s Fender tone stack can be found in the cathodiene follower tone stack in the 5F6A Bassman, which is what Marshall pretty much stuck with until the late 80s. This is a little more refined than my analogy of 3 guitar pickups, each with different volume controls, each which had different frequencies on them. But this is how it actually works. And there's a lot more to this. But if you really want to know this stuff, man, the books are thick, the math is complicated, and you got to roll your sleeves up. And this is just a YouTube video. So I hope you found this interesting and that I didn't blather too much. It's hard to sum up complicated stuff in any coherent way. And I just don't have time to script these out and revise them. So I found a few extra minutes today to do this. I put it together, stick it up there, and you gets what you gets.